Hi there, everybody. This is Mrs. Sharp. I got to turn off my jams here. These are notes 0.2 part 2. So again, on the same piece of paper or notebook that you were taking notes for the last set when we talked about units and metric prefixes, review, that kind of stuff. Go ahead and continue. I want to just note that there's really 3 things for this learning target that I'm expecting for you to be able to know and do. Units, which we talked about last time, and then today, which we're going to talk about, is significant figures. Being able to apply those rules to express uncertainty in measured values and talk about how that impacts accuracy and error in the lab. So here we go. Let's talk about significant figures. Why do we use them? So significant figures, which we abbreviate as sig figs, are all known digits plus one uncertain digit, which is the last one. So it turns out that when we measure something, we can never know for sure the exact measurement. So for example, if I'm saying I go 60 miles an hour, well, I'm going 60 miles an hour, but really I'm going like 59.8998567. You guys get the idea. There's an infinite number. We never know exactly how far because there's always one more place we could go in the decimal. So we've always got some uncertainty. So here's an example. If I have a length of 2.56 centimeters, which is a little over an inch, that 6 is uncertain. So this length is somewhere in between 2.5 and 2.6 centimeters, and it's a little bit closer to 2.6, but that last 6, we don't know for sure. Is it 2.561? Is it 2.562? We don't ever know. There's some rounding that has to happen. So if I change that to 2.5600, look at where the uncertainty is now. In this first value, I was uncertain in the tenths of a centimeter. Here, I'm uncertain in that would be hundredth. I'm losing my brain. Hundredth of a centimeter. Here, 10, 100, 1,000, 10,000. So here I have a lot less uncertainty because the uncertain digit is in the 10,000ths of a centimeter. So this is a much more precise measurement. This is a better measurement. So in measurements, the more significant figures we have, the better that measurement is. So sig figs reflect the accuracy and certainty of a measurement, and it can also impact the precision of a lot of measurements that are done on the same thing. So what do they mean? Let's look at object A here. And if I was going to measure object A with the centimeter ruler, I can see that it falls somewhere between 6 and 7 centimeters. And I could estimate where that would be. Object B would be between 4 and 5 centimeters. And maybe I would call that 4.4. But that 0.4 part, I'm not sure. I know it's between 4 and 5, but I don't know if that 0.4 part is exactly right on. Same thing here. I can say, this is 0.8, but I know it's between 6 and 7 for sure. I just don't know if that 0.8 is on. So that last digit is always uncertain to an extent because we have to estimate no matter what on the last one. Let's use a different ruler now. Here's ruler 2, and if you'll notice, I have more markings on here now. So when I look at this, that first measurement, now instead of just knowing it's between 4 and 5, I can even tell it's between 4.1, 4.2, 4.3, 4. It's between 4.4 and 4.5. So I can estimate it's really close to 4.5. So I'm going to call it 4.49. But again, I'm still estimating this last digit. Same thing for object A. I can tell now it's between 6.7 and 6.8. It looks really close to 6.8. So I can estimate that last digit to be 9, but that last digit is still estimated. We have to do that for every measurement we take. So here are your rules for determining sig figs. You're going to want to make sure we write these down, and then I'm going to stop and have you practice. So first, number 1, if a number is not 0, if it is 1, 2, 3, 4, 5, 6, 7, 8, or 9, It is significant. So I really should have a unit on this number, so we'll make one up. If this is 4,268.628 miles, let's say, maybe I'm flying somewhere and that's how many miles it is of my flight, then every single one of those is a non-zero number. So it would have, that 4 would be significant, 2, yes, 3, 4, 5, 6, there would be 7 sig figs in that number. We're counting how many there are. Okay, here's where it gets a little bit hairy. Zeros at the beginning of a number. So beginning means zeros before any numbers that aren't zero. I'm not sure that makes sense, so we'll take a look at an example. But those are never significant. So here's your first example, 0.23. Now, this 2 is the first number that's not 0. So anything before that is considered the beginning. So this 0 is at the beginning of the number. That means it's not significant. So that one doesn't count. But 2 is not 0, so it does. And 3 is not 0, so it does. So we have 2 sig figs. Whoopsie. Same thing right here, 0.044. This 4 is my first number that's not 0, which means everything before it is considered the beginning. So these zeros are both at the beginning. I'm saying beginning weird. So they don't count. So this 0 at the beginning doesn't count. This 0 at the beginning doesn't count. But 4 is not 0, so it does count. And this 4 is not 0, so it does count. We have 2 sig figs here. I'm not sure why this is randomly here. Ignore that for now. But don't ignore this part. Number 3, zeros in the middle of a number are always significant. Let me tell you what I mean by that. These 2 zeros are considered the middle of the number, both of them, which means there is a number that's not 0 to the left somewhere and a number that's not 0 to the right somewhere. So they are like a 0 sandwich. So if there's a number that's not 0 on either side somewhere, then they're considered middle of the number. So 3, 5, and 7, all not 0, so they would count. These 2 zeros are both in the middle of a number, so they would count. And this 1 is not 0, so it would count. So we would have 1, 2, 3, 4, 5, 6 sig figs. Okay, this number looks really, really similar. We're just moving the decimal. So now take a look. This 0 is not a middle of the number 0 because there's not a number that's not 0 on the left-hand side. So what that means is that this 0 is actually a beginning 0 because the first number that's not 0 is here, and it's to the left of that. So this 0 is a no. 3, 5, and 7 are yeses. Now these zeros are middle zeros because they're in a sandwich, so they count, and 1 counts. So we still have 6 sig figs. Here's another one. These zeros are considered beginning of the number zeros because they come before a number, the first number that's not 0, which is 4. So they are in front of it, so there are zeros before or the beginning of a number. So no and no. 4 is yes, 6 is yes. This 0 is sandwiched, so it's a yes. And 5 is a yes because it's not 0. 4 sig figs. Last but not least, all of these guys count because these zeros are sandwiched. 6 sig figs. All of them count. Now, last but not least, we're left with zeros at the end of a number. And this one is the trickiest. So if it's at the end of a number, it might be. It all depends on if there is a decimal point present anywhere in the measurement. So if the zeros are at the end, that means they come after the last digit that's not 0. If there's a decimal place anywhere in the number, they are. If there's not a decimal place anywhere in the number, they are not. So for example, take a look at these 3 zeros. They are at the beginning of the number because your first number that's not 0 is 3. So since they're at the beginning of the number, they never count. 3, 4, and 5 do. Now that's my last number that's not 0. So these 2 are at the end of a number. Is there a decimal place? Yeah. So they would count. So these zeros do not. They're at the beginning. 3, 4, 5 do because they're not zeros. And these zeros at the end do because there is a decimal point that I see. So 5 sig figs. All right, let's talk about rounding. If I need to take this measurement and I can only use 3 sig figs,